So last problem we did the first problem in a MIT Physics 1 exam, which was one-dimensional kinematics. We've done free fall, which is one-dimensional kinematics, the one dimension being y. We did this problem, which is another one-dimension kinematics problem, the dimension being x. And now we're going on to projectile motion. Now, projectile motion is just a two-dimensional kinematics problem, meaning we have motion in both the x and y direction. So, the big thing here with two-dimensional kinematic problems is it's really just two one-dimensional kinematic problems. And we'll work through that a little bit, but I think it's best just to start with an example. So we have a rock is thrown upwards from a bridge at an initial height 8 meters above the water at an initial speed v0 and at an angle of 36.9 degrees from the vertical as shown. Use g equals 10 meters per second squared to solve this problem. See notes on the formula sheet about the values of trigonometric functions for this angle. So there's also a PDF of their reference sheet, so we'll have this to work with. Part A says, write a set of equations for the horizontal and vertical positions and velocities of the rock as a function of time. Clearly indicate on your drawing your choice of axis and what point you are using as your origin. So let's start with that first part. What I like to do is just to go up here and draw an x and a y axis. And I like to just make the origin really big. And then I like to do this to indicate, hey, wherever the ball is where I'm saying the origin is. Okay, so that's the first thing I want to do. Now I want to look at this. We have a triangle here, where this is v0. This is v0 in the x direction, which is equal to v0 sine of theta. And this is v0 in the y direction, which is v0 cosine theta. And we do know theta is 36.9 degrees. We also know gravity is about 10. I think that's because calculators weren't supposed to be used here. I don't know. But I'm just keeping it as theta because I don't feel like rewriting it over and over again. So for that reason, that's what I'm writing down. Okay. So now what I want to do is I'm going to come over here and I'm going to start with what we know with the x motion. Sorry. And what I like to do is I like to write x initial, x final, v initial in the x, v final in the x, acceleration in the x, and then time is in both x and y. Oops, sorry, got my equal sign there. So x initial, well, we're letting the initial be our origin, so that's just 0. X final we don't know. We know v initial in the x direction because we worked it out over here. That's v0 sine of theta. Oops, I'm sorry. That's supposed to be down 1. X final we don't know. This is v0 sine theta. I'm going to skip final velocity because we know acceleration. The only thing accelerating our object is gravity, and gravity is just in the y direction. So there is no acceleration in the x direction. Acceleration is our change in velocity. So our initial and final velocity should never change. So our final velocity is also v0 sine theta. And then I'm going to do the exact same thing with y motion. I'll do y naught y final, the initial y, the final y, acceleration y, and time. Now, for the same reason, we're at our origin, so y naught is 0. Y final we don't know. Y initial is v naught cosine theta. We don't know our velocity final in the y, but we do know our acceleration is g. Okay, so we want to first find a set of equations for the position, horizontal and vertical. Well, we're going to need our kinematic equations, and we have two. We have one with velocity, and we have one with position. They might look a little different. I'll use mine, the way you're probably more used to seeing it. Well, this first kinematic equation has nothing to do with position. R is usually a position vector. That's what that means in physics. I'm going to change it to x. This is x equals x naught plus v naught t plus 1/2 at squared. Or you could use y. It doesn't really matter. Because the way you're probably used to seeing it, we'll start with the x motion, is delta x equals v naught in the x direction times time plus 1/2 at squared. Well, there's no acceleration in the x direction, so this is 0. This is x final minus x initial, but again, x initial is 0. So this is really just x as a function of time is equal to velocity in the x direction is v naught sine of our angle times time. Now, we want sine of 36.9. Sine of 36.9 is right here, and that's 0.60. So, x as a function of time is equal to 0.6, that's from here, v naught times time. So this is our x position. We can do the exact same thing for y. This is the same thing, y final minus y initial. Y initial is 0. So this is y as a function of t. This is v naught cosine of our angle times time plus 1/2 times 10 times t squared, because our acceleration is g, which is 10 meters per second squared. So y as a function of time is equal to, well, let's find the cosine of that angle. Cosine of what we want is 0.8, so we can say 0.8 v naught times time. This should be a minus because we're going down. So 10 divided by 2 is just 5, so minus 5t squared. And now we have our y position. Okay? Now, then, it wants us to find the velocities. Well, the velocities will work in a very similar way, except we're going to use this one. So velocity in the x direction is equal to velocity initial in the x direction plus acceleration times time. Again, there's no acceleration in the x direction, so that's 0. Our velocity final in the x direction is then just v naught sine of our angle, which we know is 0.6 v naught. Okay, and that's really what we expected because the velocity never changes in the x direction because there's no acceleration. Now, for the y direction, it's a little different because velocity in the y direction is v naught y plus at. There is acceleration here. So velocity in the y direction is going to be v naught cosine theta minus 5 times time. Or cosine of our angle is 0.80 minus v naught, minus 5t. Okay, so for this one, we just use our other kinematic equation. So now we represented the position and the velocity of everything. This is really important because you'll work with something later in physics called the Lagrangian, and it's important to know both the position and the velocity. But obviously we're not doing that yet. This is just part A. Now for part B. The rock reaches its highest point in 2 seconds. How high is the rock above the water at that instant? Hint, first you need to find v naught. So here's the conceptual part. When you have, I'll draw it over here. When you have some sort of projectile motion, let's say it looks something like this. At some point, you'll reach your highest point. And at this point, your velocity in the y direction is 0. That's going to be a very important kind of trick to know. So, here's what we're going to do. We're going to reform this, and I'll do it in a different color. I'll do it in green. First off, we know the time is 2 seconds. That was given to us in the problem. And our final velocity there is going to be 0. So, with that in mind, let's use our kinematic equation with velocity. So, again, we know Vy equals V naught y plus AYT. And this is 0 at max. So 0 equals V naught, this was cosine of theta, minus 5 times t, 10. And in fact, this should also be 10, this shouldn't be 5. Why do I keep confusing that with 10 and 5? I did that twice. There we go. Oh, I know why, because this was 5. Yeah, but that should actually be 10 because we're not dividing that by 2. My bad. Okay. Okay, so we got this, and we know that this is equal to 0.80 V naught minus 10t, because we know what the cosine of our angle is. 10t equals 0.80 V naught if we add it over. 10, we know time is 2. Divided by 0.80 is equal to our initial velocity, which is about 25 meters per second. So this was our initial velocity. Okay. Now, why was this important to find? Well, hopefully you would have seen, we're looking for position, so we're going to use delta y equals v naught yt plus 1/2 AYT squared. This is a great equation to find position. And what you probably would have seen is when you try to work through this, you're going to have trouble because you don't know, right? So again, this is y final minus y initial. Y initial is 0. So y as a function of t is v naught, cosine of that angle, times time, minus 5t squared, because this is 10. The problem here is you don't know position, and you don't know our velocity here. But we know now that it's 25. And we also know what this is. This is 0.8. So y as a function of time is 0.80 from our cosine function times v naught, which is 25, and our time is 2, so times 2 minus 5 times 2 squared. So this y, when your time is 2, is going to be 20 meters. Now, what is this 20 meters above? Well, that means you're 20 meters, maybe it's here, for example. But our origin was here. So you're 20 meters above the block. 20 meters above block. But specifically, the question wants to know how high are you above the water? Well, the block is our height, and that's 8 meters above the water. So all we have to do is 20 meters plus our height, which is 8 meters, equals 28 meters above water. And there you go. That's all there is to it. Hopefully that makes sense. This was a really good problem. I like it. I hope you guys like seeing these. And I'll keep doing them.